Okay, this is a football situation, as you can see, right? The crossbar in real football, not soccer, but real football, you have to go over, not under, right? So there's a place kicker that kicks the ball. At that, I have an animation. Okay, ignore that circle for a while. Actually, I'm gonna see. If you kick it harder, this is the initial direction and the speed of the ball, and then the ball will follow this path like that. So like imagine you are holding a garden hose. All of the water molecules actually traveling in a line so you can see the path. You know what I'm saying? So that's the same idea. So if you kick it harder, give more velocity, of course it's going to go farther. However, it also depends on the angle. With the same speed, 21 meters per second in this case, I have the speed right here. That's why I drew this circle. And then see if you kick it a little bit higher, 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 higher. Oh, there, you make it. Oh, you still make it. This is one of my examples coming up. But eventually, if you kick it too high, then whoa, it just falls right back, right? This is what's called punting in football. Kick it high, hang time matters. So we have to derive the governing equation of this. And then we kind of did it earlier, x and y separately. Those of you physics people, you have seen this projectile motion, okay? And then, of course, this football is played in vacuum with a bunch of robots. Because if there's an air resistance, it doesn't even go anywhere near close to this path. I mean, that's like huge, huge difference in like football kind of sports. So ideally, this is done in vacuum, okay? Okay then, shall we derive this thing? Okay, and then did you know that most of the laws of physics, I think all of them, happens to be solution to a differential equation? Really? Yeah, watch this. Let's set up the differential equation. Your acceleration vector. Oh, by the way, acceleration is a second derivative of the position vector now, isn't it? Yeah. Is equal to, what is the only thing acting on it with our assumption that in vacuum and the other force is the downward gravity? You get it? So negative g j vector. That's it. That's our differential equation. Simple, isn't it? Okay. Since this is a second derivative, it's what's called a second order differential equation. It requires two different constants. You'll see why. So here comes the first constant, velocity at original time at the beginning when we start the stopwatch, when the kicker kicks the ball, happens to be, well, most of the people, and you learn from homework, that is the magnitude and the direction, isn't it? Speed and the direction is how the lay people, not mathematicians. Only mathematicians think in terms of the component notation, vector components. You know what I'm saying? So at that speed, which happens to be for us just a v naught, and then that angle theta, whatever that is. Okay, we'll get specific on the next example. Then we have to calculate the components of these things, right? So let's calculate the components. Right triangle right there. So this is velocity x component, which happens to be v naught and cosine theta. Do you agree? And then this y component right there happens to be, rotate the tablet and write it sideways. Vy here is equal to v naught and sine theta. Good. Okay, now then let's talk about this initial condition. Since I started writing with red, why don't I change the color to red? Okay, so that is v naught and then cosine theta, I vector, correct? X direction, I vector, and then plus v naught sine theta and j vector. Good. You notice that this is pure constant. It does not have any t term in it. Only t comes from this differential equation. These are just initial conditions. Second initial condition is, where are you launching this thing? Okay. I mean, you could launch it from the top of the building. Any other application is possible. However, we'll adjust it. We'll always place this at origin. Do you guys know what that is? That is the zero vector. What does zero vector look like? This, of course, right? That's still a vector. Magnitude 0, but it's still a vector, okay? Now, what happens if it's at the top of the building, right? And then this is a ground down here, and this is like 10 meters high. What happens? Then this line is y is equal to -10. We adjust it like that. That's for our sanity's sake. Otherwise, what we're doing is algebra gets crazy. Okay, you can place the origin here, or you can place it up there. Place it up there, okay, if you know what's good for you. Okay, so there's that. So it's always done. And in case of football, that's why I took football example. You put it on the ground and kick it, so it's 0, okay? Alrighty, now shall we solve this differential equation, see? Yeah, let's do that. So back here, so this A, by the way, A happens to be second derivative, right? Second derivative of the position vector. Some people put t here. I mean, it's like some people put it up there, some people put it here. Is it so annoying? I think it's okay, right? Just to make sure you know that this is a function of t. Okay, negative g, there's no t, j vector, and that's it, right? We take an antiderivative. Antiderivative of this second derivative, of course, is single derivative, isn't it? T. And that's what we call velocity vector, correct? And this becomes negative g t, j vector plus constant, and that constant is a vector. You get it? Everything is a vector in this chapter. You with me? Okay, let's evaluate the initial condition. At velocity is equal to 0 initially, which means you substitute 0 for t. You know what I'm saying? So this thingy just becomes c, correct? However, from our initial condition from the problem, that should be v naught cosine theta I vector plus v naught sine theta j vector. Good? That tells you what c is, huh? We plug it back into differential equations. So what we have is now v is equal to, that t looks weird. Okay, now there's a I term, there's no I here, so remember, imagine that thing is all in here. So we just have v naught cosine theta and then I vector, and then there's a j term and there's a j term. So these are the like terms, they behave just like variables and become j's become like terms. So we have v naught sine theta t minus gt j vector. Are you with me? This much? Good? No confusion here? Okay, these are velocity x component, velocity y component. You get it? Okay, then now we integrate one more time, and that gives us r, correct? Because this v was dr dt. Now, so we have v naught cosine theta t. When we write it like this t is not argument of cosine, it's separate, cosine theta parenthesis t. Okay, Kara.
In the velocity one, where did the t after sine theta come from?
Oh, because I just screwed up. It's not there. Nice catch. I jumped the gun. That's the next line. How about that? Better? Okay, so there is t now. Nobody is saying, oh yeah, that becomes sine and this becomes negative cosine. Nobody's doing that, right? Because our variable is t. This thingy underneath matters a lot, right? Okay, the sine theta and v, they are all constant. Once you kick the ball, it's out of your control. You cannot control it no more. You cannot change that angle. That's the initial angle. You know what I'm saying? Okay, t is our only variable, and x and y. Okay, then minus, and this thing becomes g t squared, therefore 1/2, right? And then we need another constant. Should we call it d? C2, C1, whatever, anything but C, right? Now let's call it D. Okay, now we'll apply the initial condition again to find that. In order to, you have done this before in chapter 6, not in vector functions, but you evaluate it, right, like that. And of course, if you plug in T here, 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 they all die. It just gives you D, right? However, from our initial condition, that needs to be 0 vector. Good. So D is equal to 0. Therefore, our projectile motion happens to be, oh, it's a computer, so I can do this. Video. This is our projectile motion. How about that? Okay, Kara.
I think you forgot the I after the cosine theta t.
Why do I keep screwing up, right? Yes, I did. I think I can move the whole thing and save it. Nice catch again. Like that, right? And then I'll put parenthesis and then I. How about that? Better? Okay, alrighty. So far so good? Okay, now our next interest is, this is nice and all, right? So here, this thingy, what we have here, happens to be x as a function of t, and this thingy right here, the all of it is y as a function of t in parametric motion. You get it? We like to eliminate parameter t and have a y as a function of x. Well, why would you want to do such a thing? Many times, see in this field goal problem, I kind of showed it to you. There's a range of angle. Now, you can kick it this high, this high. Oh, you make it, you make it, you make it, you make it. Good, 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 good. Nope, you don't make it anymore. I like to know that range of angle. And then if I have too many variables, t, and then now we're like kind of varying theta, and then, oh, God, that's just too much systems of equation now, isn't it? So in systems of equation, we eliminate variables. So why not just eliminate t right now and have a nice relationship between x and y? And clearly, the way you see it, you need an upside down parabola. And you've been told that since algebra 1, the projectile motion obeys this upside down parabola, right? Well, now you get to see why. So let's do that part. Shove this thing down, right? Okay, let's do it. So since I said this is x and this is y, I'm going to write it here. So our x is equal to v naught cosine theta t, and our y is equal to v naught sine theta t minus 1/2 gt squared, eh? Why don't I solve this thing for t and then substitute it here? That's how you do elimination, right? So that is x over v naught cosine theta, eh? Substitute it here, and let's see what happens. So v naught and sine theta, and then we have x over v naught cosine theta minus 1. I'm going to write g over 2 to save space. That's too close. G over 2, and then x over v naught cosine theta squared. Okay, you with me? Okay, let's see what this thing becomes. V naughts cancel, right? So we have x sine over cosine, that is tangent. Oh, that's remarkably pretty now, isn't it? Next one is the ugly term. Okay, g x squared, right? And then in the denominator we have 2, and then v naught squared, and 1 over cosine squared. Let's just write that as secant squared. Okay, it is what it is. Okay, this is your y as a function of x now. How about that? Okay, let's apply it. First example is the maximum range. Meaning, do you guys who ever played ball, you instinctively know, or your coach taught you, at what angle are you supposed to throw the ball from horizon to make it go farthest? I know you're nerdy, so that's why you're taking 5th period math and don't play sports, but hey, tell me that maximum launch angle.
Is it 45 degrees?
Mm-hmm. You kind of, if you ever throw a ball, you don't want to throw it straight. I mean, it goes there faster. But if you want to go farthest, you have to kind of throw it up, right? It's 45 degrees. Shall we prove why that's 45 degrees then? Yes, we shall. Okay. So we want to maximize this. Now t has been eliminated, so we are just looking at the path of the curve here, right? I want to maximize this length. One thing I notice is y value is 0 here and here, isn't it? So let's set y is equal to 0. And then we can have, I mean, this is technically a multivariable function, but depending on what you hold as a constant, we can think of it as a single variable calculus. So maximum range, meaning set y to 0. How about that? Okay, let's do that. So then what we have is x tangent theta, send it to the other side, is equal to, no, that's not, minus, then g x squared, that's squared. See, I'm about to erase that thing, so it doesn't matter, but 2v naught squared and secant squared theta is equal to 0, right? Can we common factor x? Because there's an x here and there's x here. Yeah. So let's do that and then knock off one of the power. Are we good? So what that tells you is xi is equal to 0, or this whole thing is equal to 0, right? Okay, push this thing down a little more. So that whole thing is equal to 0, meaning well, I was gonna do it in my head, but children may get lost, so let's not. Good. So x here is equal to multiply 2v squared divide by g multiply cosine squared. What is sine times, and what is tangent times cosine squared? Oh, come on, people.
It is sine cosine.
Yes. Oh my God, children. Sins of the past still haunting you, huh? I know. See, calculus is very easy subject as long as you got your algebra, geometry, and trig figured out. Right. I mean, always just like this. Our past is always haunting us, right? Yeah. Okay, we can set that to 0. Well, take a derivative and set that to 0, but. 2 sine theta, cosine theta. Why does that look so familiar?
Sine 2 theta.
Oh yeah, so we can Yeah, we can just convert it like this and change that to sine 2 theta, eh? Now we know when the maximum of that is without even taking the derivative. This is constant, right? Once you kick it, you cannot adjust the speed anymore. That's your initial velocity. G is constant. So this is the only thing. Sine theta, this is maximum when sine 2 theta is equal to 1, isn't it? So you can say max at sine 2 theta is equal to 1, which tells you 2 theta, then of course it's 90 degrees, which should tell you then theta is equal to 45 degrees it is, right? How about that? Amazing, isn't it? This proves if there's no air resistance, 45 degrees gives you the maximum range. Any of you play golf here? Oh, okay, so maybe golf is a bad example. If you launch it up at 45 degrees, that is really, really high, and it doesn't go anywhere. But what is the ideal launch angle of a driver? Driver is the big stick that sends the ball farthest. Do you know what the maximum launch angle of that is?
Can I take a guess?
Yeah.
I'll say 30 to 35. Probably 37.
30 is about right for amateurs like me. Professionals have it like at below 20. But why? Why is it so much shallower than 45 degree angle? This is like pitching wedge. My pitching wedge is at 45 degree angle.
I might know.
Okay, somebody. Matthew?
Is it because the head of the actual golf club is angled so it propels the ball upward at 45 degrees?
No. Actually, my head is 10.5 degrees. But I hit it upward, so actual launch angle is about 30 degrees. In case of professionals, it's much, much shallower because they go faster. There are a couple of things that's going on in the golf ball because like some of the world problems, they use the golf ball. Okay. Golf balls have backspin. You know that the golf balls have dimples, right? Golf balls have dimples. And then when you hit it with any club, driver does not put too much backspin, but still there's a backspin. It kind of glides and curves. So especially when somebody like Tiger Woods hits it, it actually rises in the air like that. And you achieve that maximum angle here, not here. You know what I'm saying? And then it actually glides a lot farther than the regular projectile motion. It stays in the air like almost forever. And then here's another thing. Once it lands, it has to roll, right? What we just calculated does not count for the roll. But actual distance in golf is rolling distance plus the carry distance, they call it. You know what I'm saying? All of this, in order to maximize it, you don't want to hit it too high. Right? So it's like between 20 and 30 degrees is the ideal launch angle for amateurs like me. Okay. So it's like, and then air resistance and a lot of things come into play here. But in vacuum, and if you're just purely measuring the flight distance, then 45 degrees, right? Because in case of like baseball, somebody's going to catch it at the other end, right? So you don't want to let it roll forever. That's not how you play baseball. You get it? Okay, then let's try to kick field goal. Okay, in this problem, you're kicking it at 21 meters per second. I think that's the maximum leg of that kicker. And the goalpost is 10 feet high, so like about 3 meters. Okay, 40 meters away, about 45 yards-ish, which is a typical distance of NFL kickers in a game. They actually, this is easy. This is chip shot to them. Okay, let's say this is like high school football. Then let's try to animate this a little bit. So that's why I drew this circle so that it gives me 21 meters per second launch velocity. So that's too shallow. So go up, 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 up. Almost. A little more. There, right? About 40 degrees-ish. Then you will barely hit the crossbar. So you have to kick it higher than this. So it's greater than this. And good, you make it easy, easy. Okay, good, 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 good. Wait, it's getting bad, bad, bad. Wow, right there, about 55 degrees-ish, you will hit the crossbar again. And after that, this is too high. You know what I'm saying? So we want to find this range between about 40 to 50, was it 3 degrees? Yeah, we want to have that kind of answer analytically without doing this. Because none of you have this thingy, right? Okay, let's see how that can be done. This is one of the harder problems. Okay, so velocity is 21. So we'll say this x downrange here is 40 meters. This way. And this goalpost is 3 meters high. This y here is 3 meters. You know what I'm saying? And this velocity, initial velocity is 21 meters per second. And this angle, we don't know. That's what we like to figure out. Do you understand the setup? Okay. Now, this is equal to y, so our, well, let me go make a copy of this function that I figured out. Where is it? Where's my y? This one, right? This is what I need. So let me make a copy of this. Okay, we'll use this. Do you see that this, my y needs to be greater than 3, right? Because if it's exactly 3, it's going to hit the crossbar and it's no good. So my question here is this y needs to be greater than 3. This entire thingy has to be greater than 3. Do you see that? Okay, so let's do it. I'm going to x is equal to 40, but we'll just keep it as x. So x tangent theta minus u. This is ugly term, right? Yeah, somebody have the calculator. We're going to let k is equal to gx squared. G is 9.8, x is 40, over 2 v naught, and v naught is 21 meters per second. Somebody punch that and tell me the numerical answer. And store it into k while you're at it. Oh my God, this high school's reputation is on the line. Somebody just, will you please do it? What?
17.7 repeating.
Good. Okay, and store that. We're gonna need that later. Okay, then we'll just write it as k. You know what I'm saying? So we have k now, that's k over there. This is common practice, especially in physics, because there are so many variables floating around. This thing needs to be greater than 3. We have to solve that inequality. Are you with me? What is our variable here? Our variable here is theta, right? At what angle? Okay. Do you see this is a quadratic form? Tangent theta minus k, and we convert this into, oh, here we go, last year's review, right? Trig equations and inequality, eh? Yeah, okay, then do you see that negative k tangent squared theta plus x tangent theta, I mean, and then minus k, right? Bring 3 over, minus 3 is greater than 0. Say yes. This is ugly, right? Multiply -1 on both sides. I mean, you could just take an eraser and do it, but hey, I got a computer. So change the signs like that and change the direction, eh? You with me? This is still very ugly, isn't it? Okay, K is at 17.7 repeating. This is 40. And so this must be, oh, I forgot to change the sign of this, right? That's ugly. So this is 20.7 repeating. You get it? You guys still have a quadratic formula program that I taught you? Somebody who has that program, run it and tell me what these things are. And then let's review quadratic inequality. We have 2 zeros, right? Tell me what those zeros are. Oh, come on, people, hurry. And we don't want equal signs, so let's just have an open interval. None of you have that program, huh?
I have the program, but my calculator is elsewhere, unfortunately.
Okay, fine. I'm just gonna go off of a Dropbox note. This is 0.81. My handwriting is so bad. 81325 I believe is this one, and the other one is 1.436 and 247. Okay, and we want less than, so it's below here, this part, correct? Instead of these two. So we should take this part as our solution A. Do you see that? Okay, so our solution, this is tangent theta, so point, what is it? 813257, and then here's tangent theta, and then 1.43, that's 3, 6247. You get it? You with me? Now we take, can you at least take somebody inverse tangent of these two numbers? Inverse tangent here, 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 you know what I'm saying? Then we have theta. Never mind. 39.13755 degrees here, and this becomes 55.15294 degrees. Wait a minute. From our simulation, we got about 40 degrees to 50 something degrees, right? This is remarkably accurate now, isn't it?
Mr. Kim.
Yeah.
I got slightly different numbers for both angles.
Okay, what did you get?
I got 39.11997.5.
I think it might be the truncation error, because you entered this, and then when I did it, I actually had the computer store all 14 digits.
Oh, okay.
Okay. Oh, at this time for the future, many of you will be majoring in this stuff, right? So let me mention something about something called the truncation error. That's why we always make you put approximately equal to, because computer will store 14 digits. But if you round it as 6th digit, then rest of them went away, right? That's called the truncation error. And when you take inverse tangent, and this is a big theory in applied math, the error propagation. Does the error get bigger or smaller? I mean, is it at least stable, under control? You know what I'm saying? So even if you keep all of the 14 digits, there's still, machines will always have truncation error because remember this is repeating decimal, 17.7 repeating forever. You have to cut it off at some point, which creates a truncation error. You get it? Yeah, it's a big deal in applied math, computer science, engineering, right?
Wait, Mr. Kim.
Yes.
Just wondering how are you supposed to put approximately if it's inequality, or do you just not put it?
You can't. This is the best you can.
Okay, thank you.
Okay. Good. Or you can say verbally data is approximately equal to 39 point blah 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 2. The data is approximately equal to 50. Then this is it. I'll be glad that you can do this much. Okay, you do understand what error propagation is. Each time you do something to it, right, that error may or may not grow. And if this error grows exponentially each time when you do something to that equation to compute next line, we're in trouble. So this is a big deal in science. If you write a lab report, you have to know how your error grows and you have to compensate for that. Okay, and we're continuing with projectile motion. Okay, so let's read this question together. Stone is thrown from the top of the building 30 degrees to the horizontal and initial speed of 20 meters per second. So let's start sketching this thing. So here's, let's say it's a building. Okay, and we throw a stone at 30-degree angle. So let me sketch the initial velocity. Okay, let's put them right there and kind of like that, right? So what we have is initial velocity here is equal to 20 meters per second. And this angle right there is 30 degrees. So far with me? Okay, now, and then the height of the building is 45 meters. Okay, so let's throw the rest of the stuff in. So this is the ground. Okay, now we have a decision to make. And the decision is this. Do we call this y to be 45 meters here, and this to be 0? That's option 1. Option 2 is we put 0 here. Y is equal to 0 here, and then we put y is equal to negative 45 here. Which is wiser thing to do? Is my question. What do you guys say?
The second one?
Second one is much, much wiser. And this is why. I'm going to write down this projectile motion. X is equal to V cosine theta times T. And Y is equal to V sine theta times T. This T is not inside the sine and cosine. And then minus 1/2 GT squared, right? And then do you remember sometimes we eliminate the parameter T and have a Y as a function of X and many of those things, right? If I set this to be 0 down here and this is initial height of 45, then that actually enters this equation. You have to have a Y naught term. And that complicates our lives a lot, algebra-wise. So most sane people will put the origin right here. This is the origin. And you adjust this ground to be negative 45 meters. You get it? Because we, the scientists, get to decide where the origin is. Okay, so this is a wiser choice. I mean, the other way, I would accept it. If it's mathematically correct, I will take it. But I mean, they tend to backfire a lot. Okay, and then this motion will go off like that. And then it will land something, that one is ugly. I don't know why I care about these cosmetics a lot, but this is what's going on. So far, so good? Okay. Now we'll answer the question. Although I have these numbers worked out already, but have tried to have a calculator standing by. Let's do A. So part A, how long does it stay in the flight? Meaning in the air, right? So on the ground, y is equal to -45. So should we substitute -45 here? Right, so we have to have y is equal to -45 meters. Okay, I'm gonna substitute it. So what we have is -45 is equal to v is 20, right? And then sine theta, sine 30 is half. So this thing just becomes 10t, correct? Okay, and then minus g is 9.8, half of it is 4.9. Good. So this thingy becomes quadratic, 4.9 t squared minus 10t minus 45 is equal to 0. Are we good? Okay, and you guys still have that quadratic formula TI-84 program, right? Execute that program and you should get
4.21805.
Very good. 49, 6 digits. So you should get that. So far with me? And we'll call it like T1. I use subscripts a lot, or T5 or whatever, T1. Okay, so that's A, and store that. Of course, you will get two answers, one positive and one negative. Negative one is the other one, which doesn't even exist, right? Time starts right here. Okay, so B, how far away from the building does the stone land? Okay, so we want this distance, right? I'll do B here. So you notice that that is just substituting this T1 that we got here back to this equation. Yeah, it is now, isn't it? Actually, I'm going to write B1 here. I mean B here. So that's just substituting that thingy back into this and punch the numbers, then you get
73.058750.
058750 is correct. You know what I'm saying? So this is x of T1. Okay. So that's A and B. C is the hardest part. C. I'll do C in blue. When this thing falls, then it's gonna hit this ground with a certain angle and the velocity. I'm gonna draw that vector. That vector is going to look like this, right? That is what I call V. Let's say, well, just V, final. Okay? We need that velocity vector. You get it? So let's calculate it. V at any given time. Do you remember vector function? And this is like x component, y component in it. That's the vector function. We just literally differentiate that thing. So if I differentiate the first term, then it's going to be, don't put v negative v sign. No. T is our only variable. So v cosine theta. And then y component is v sine theta minus, I'm not going to have enough space there, so I'm going to bring it down a little bit. And then minus gt. Okay? This is our vector function. So after when I plug in v1, I mean t1, my handwriting is really ugly today. I'm going to zoom in. V and T1. So this is V of T1. You get it? And that thingy, I'll just look up from the notes. 17.32. See if you agree with my answer. 320508. Okay, and the y component is negative, it's downward 31.336879. You guys concur? And even then, you have to write down the unit. So far with me? Okay, so that is the velocity vector. But then only mathematicians think like that, right? We need the speed and the angle, okay? So I'm gonna draw this thingy a little bit bigger. So if I have that vector component, like so. Okay, what we are trying to figure out is, this is your Vx and this is your Vy, isn't it? And I'll call that angle phi. It's ugly phi. Phi, since I used theta already. Okay, so let's calculate the speed. Speed here is equal to, approximate, is equal to, it's just this thingy, right? Vx squared plus Vy squared, isn't it? This is Vx and this is Vy. You with me? And then you run the calculator and you should get
35.80527.
80528
Yes.
meters per second. Good. What's wrong with my handwriting today? It's extra ugly. Okay, and then how do you get the angle? Well, tangent phi is equal to Vy over Vx, isn't it? Oh yeah, huh? So your phi is inverse tangent of this thingy, which should give you negative
61.0697099.
Okay, let's round it like that. You get it? That's complete solution. Any questions? Okay, let's move on to the second example, which is angle between diagonals of the cube. What? And the one of its edge. Do you have a picture in your head? Why don't I draw one for you, right? Okay, here's a cube. Okay, and then I'm gonna copy that thing. Okay, let's try my best to. Okay, and then. That last one is not behaving the way I want it to. Okay. And then we have a problem. Is this cube, which is the backside? Is that the backside or is this? I know, that weird effect, right? I'm gonna draw the diagonal vector. This is a diagonal right here. You know what I'm saying? So that's the back corner, this is the front corner. Do you see it?
Mr. Kim?
Yes.
Maybe this will make it easier to remember, but if you like use a different color marker and trace over those lines that are on the front, that might make it like clearer.
Hold on. Oh, I just make the back one No, okay. I'm gonna do that. I'm gonna do something. What? Okay, I'm gonna give. I was going for the drama, but okay, fine. What we are going to do is put the coordinate axis right here. Is it better? So that's clearly back, and this is in the front.
Okay, yeah, that makes sense.
And then we are going to find the angle of that diagonal to one of the axes. So let's just make it this one. Okay. Does everybody know the name of this vector? This is your I vector. You know what I'm saying? I meaning 1, 0, 0 vector. Get it? Unit vector in x-axis direction. Did the problem get much easier? And of course, what should we call this vector? How about D for diagonal? And then D vector, of course, is 1, 1, 1. Do you see that? Say yes. So how do you find the angle between two vectors? You can still remember, right? Say I times D, is it equal to magnitude of I? What is the magnitude of I? It's 1, isn't it? That's fancy one. Fancy one. 1, and then D and cosine of our angle, isn't it? And that's what I'm calling theta. Good. So our cosine of theta is equal to I dot D over the length D. You get it? Okay. Tell me what I dot D is. There are the vectors. 1. Useless kids. Okay. And then the length of D. Length of D, of course, is √3. You with me? Vector 1, 1, 1 has a length of √3. Pythagorean, super Pythagorean theorem, if you will. So our theta is approximately equal to inverse cosine of 1 over √3. That should be 54.7356 and 10. So number 3, let's see what number 3 is. A projectile is fired, initial speed of 500 meters per second, an angle of 45. Let's stop right there and start drawing. Because whenever you see this, you have to draw these things, right? I mean, if I cannot do it without drawing it, what chance do you have, right? So here's the situation, and then we'll put the initial velocity right here at 45-degree looking angle like that. Okay, let's put that in blue color. So your initial velocity, V, let's say, is 500 meters per second. Good. Okay, and this projectile will then fly in this kind of path. So far with me? Okay, now let's continue reading. A, when and how far away will the projectile strike? So, part A, you have to talk about the flight time, right? And then also, how far away, right? Oh, actually, when, yeah, okay, we'll do that. Okay, so let's write down this governing equations of projectile motion. Right? I'm gonna put the work glove on. So x is equal to v cosine theta t, and this t is not part of cosine, argument of the cosine is cosine theta, and t Okay, theta is 45 degrees. Like that, right? It's fixed. Once it leaves, you have no control over it. And then y is equal to v sine theta t minus 1/2 gt squared. That much we should know by now. Okay, now at ground right here, right? Do you see that y is equal to 0 at this point? Y is equal to 0 at 2 points. One of them is here when you fired it, and the other one is when it lands, correct? So what we have to do is set y to 0. Good. Okay, so we have 500 and then sine 45 times t minus 1/2 and then 9.8 times t squared now, right? Say yes. Somebody have the calculator standing by. Factor out t. So we'll have t, and then this is √2/2, isn't it? Say yes. Sine 45 is √2/2, because you learned that before the pandemic last year, so you should know this much, right?
Yeah.
What's the meaning of that facial expression? Like what sine kind of look thing? So we have 250 √2. Good. Minus, and this is 4.9 t is equal to 0. Oh, I forgot to write is equal to 0. Okay, so first of it, that means t is equal to 0, which is this point, right? Or that's not the one we are looking for. This is the one, right? T is, let's just push the calculator all together and somebody tell me what that is. Or somebody who did homework from your homework, tell me what that becomes. Oh my God. Seriously?
72.153.
Wait. 72? That's kind of big. No, there's no way this thing stays in the air for 72 seconds.
I got 72 too.
What's going on? 72? Oh, actually, it's 500 meters per second. Oh, this is supersonic. Yes. I think it's correct. Okay. 72 and point, what was it? Somebody repeat it?
153753. Oh wait, yeah.
Okay. Store this, okay? We'll call it, we'll call it T1, okay? Store it because we need to calculate how far, right? And what you do is, the range is x of T1. You plug that into this T, and then you compute. You know what I'm saying? Okay, so what do you have? Oh, come on.
25,510.20408.
25, and what?
25510.
510.
0.20408.
20408,
Yeah.
like that. Dang. Okay, I'm gonna make a little more room. that is not a realistic 25 kilometers, right? Wow, so this is a rail gun. Okay, this is not, I mean, totally not so realistic situation. Actually, 25 kilometers is not really, it's like really big gun. Huge artillery. I mean, not that the US military does not have a gun with this kind of range, they do. But okay, couple of things. When you are firing it that far, I think with this kind of distance, the curvature of the Earth comes into play. And not to mention the air resistance, but let's say this is some other planet equal size of the Earth without any atmosphere, right? Because the air will come down really, really fast. But the curvature of the Earth slightly helps you because imagine this part is bending like this down, and so it stays in the air a little longer. So if you're firing a rail gun, and then of course you guys know what Coriolis effect is. Earth literally rotates on you while this shell is in the air. So you miss it to the right. If you are firing it in northern hemisphere, and if you're firing east or west, it doesn't bend. But both directions, I mean, the weird physics from the north to south, and north to south is easier to see. If you're sitting at a north pole, and then fire this mega projectile southward, and Earth rotates while it's in the air, so it's like it's going to hit somewhere a little bit right of what you aim for. But if you fire it northbound, it aims to the right as well. Think about it. It's one of the weird things. It's called Coriolis effect. And then artillery people, you have to compensate for that too. Especially with this kind of range, it's going to curve quite a bit in the air. And of course, the wind and everything comes into play. So it's like, this is really a true science to fire these artillery shells. Okay, so that's A. Let's do B now. B. How high overhead will the projectile be when it's 5 kilometers downrange? Okay. So 5 kilometers, the whole thing is 25, so let's say 5 kilometers here. I'm gonna throw the line somewhere here, right? Let's say this is a 5 kilometer mark. And then we want to know how high this thing is, right? That's what they are. We'll call it Y1. Good. Okay, so I'm gonna do B in blue to color coordinate. Okay, so in B, X is equal to 5. You know what I'm saying? Then we have this thing, so our T is equal to X over V cosine theta, isn't it? And for us, that is 5 over V, what is it, 500 cosine together, so it's 250 root 2. Good? Say yes. And somebody tell me what that is? How many seconds?
0.014141.
Wait, that's that fast? You guys concur? 0.012?
0.014142.
I know this is supersonic flight, but dang, that's fast.
Do you have
You
to
guys all,
change X into meters?
huh?
The speeds in meters?
Oh my God. This is in meters, right? Yeah, that's our screw up. You see, this is kilometer. So what we have to do is add 3 zeros, right? Does that mean it's 14 point? Yeah, 14.142, yeah. 14.142. Somebody give me 3 more digits.
136.
136 seconds. Okay. Store this, and we'll call this T2. Okay. So far, so good. Because we want to know how high it is now, right? So the height is, we plug into T2 into this Y equation. You get it? And calculate that and tell me what that becomes. It should be 4,000 something-ish, but I want the exact number. Oh, come on, people. We are on recording. The reputation of this high school, notice that I left the name of the high school out, but reputation of this high school is on the line. You're not the only people watching this video, okay? I just give this away as a community service to everybody who wants it.
I got 490.2.
490, that's short. Maybe 2, and then give me other digits.
It ends at 0.2.
Exactly. Oh,
Yeah.
wow, dang. With a G and everything. Oh, well, okay. You guys concur?
I got 4,020 meters.
Yeah, that's like what I had.
Because if it's going 500 meters a second
Yeah,
in 14 seconds.
4,020 point what? Exactly 4,020?
I think it rounded off, or I just forgot to include the decimals.
Can somebody give me 6 decimals?
I got 4019.9999995.
4019.9 repeating, like that?
And a 5 at the end as a 6.
99999 and 5, like that?
That's what I got.
Okay. That's like, I got 4020 on the Dropbox note, so this looks more like it.
Wait, so you plug that into the original?
Yeah,
formula,
Y.
right? Y equals V sine. Okay.
Okay, so far so good. What I usually do is that something like this, I save it as a Y1 in the calculator so I can compute this fast. Okay, but then I have a little programming background. So what is the greatest height? Okay, so part C is this. I'm gonna do part C in green. So we're looking at this point right there, right? We'll call that Y2. Okay. And then at this point, we calculated T2, so we'll call it T3. Maybe we should have called this thing Y. Let's change the name for these things. I'll call this Y3 then, huh? Just coordinate it, and then go back and change this to Y2. How's that? Okay, so that's T2, yeah. So this is Y2. You know what I'm saying? That too looks ugly. I don't know why I'm like this, but okay, so let's do that. Okay, at the highest point, right? There are a couple of ways to get it. Number one, we can differentiate this and set it equal to 0, or we have this thing already, right? So we can divide that by 2. Which way do you want to do it? Of course, divide this by 2. I mean, I can do it either way. Let's do it calculus way, right? Yeah, let's do it calculus way. So velocity in y component. Velocity in y component is, and take a derivative of that thingy. So we'll have v sine theta minus gt. You with me? And then we have to set that to 0 at the maximum height. You know what I'm saying? So what we have is t is equal to v sine theta over g. With me? So to us, this is still, wait, too fast. What was the initial speed? 250. 250 root 2 over 9.8. Okay, somebody tell me what that number is. Actually, I think I have it. See if it's correct. 36.076877. Do you guys concur with this number? Okay, and then, of course, we plug that back into, this is y3 now, and we'll call that t3, into our original y. You know what I'm saying? So we'll have 6377.551021 meters. And this totally unrealistic high school physics kind of railgun experiment. There's so many things that will go wrong with this calculation. It's not gonna, I mean, it'll literally miss the target by miles, okay? With everything else considered, it's not going to be, I don't think you will hit the same city with this kind of targeting. Okay, any question before we move on to number 4?
Mr.
Yep.
Actually, I don't need number 4 anymore, because the example for today's lesson, I think, on the Dropbox is the same type of problem.
Yeah, it's exactly the same thing, huh? Okay, then let's skip number 4 and move to number 8 then, huh? Okay, let's do number 8. Okay, so electrons in tube. The TV that we are talking about is not the TV that you kids grew up with, which is usually called flat screen, right? Do you know why those people still make big deal about flat screen colored TV? Have you ever seen any TV that's not flat and that's not colored? Have you seen black and white, this thing called cathode tube TV? At least on YouTube somewhere in the olden days, the TV used to be bulk, big box. I mean, I have one sitting in my classroom, but that's still projection, so that's still not cathode tube. In the olden days, and it's not flat, it's a little curved. You have no idea what I'm talking about now, do you?
Are those the big TVs that all the teachers
Yeah.
have in like the corner?
Yeah. Do they still have those?
I don't know. I haven't been to school.
I don't know. Last year, do some teachers still have that at the corner, right, hanging? Yeah, that kind of TV is what we're talking about here, okay? Because these flat screen TVs are only about 15 years old or so. I mean, maybe 20. I know it's not quite 20. Because I got this mine that I'm looking at and using it as a gigantic computer monitor. I think I bought this about 15 years ago, so it's like it started coming out about 17 years ago. And the TVs back then were small but bulky, like kind of what you see in some corner of the classroom. Okay. The way that works is there's a electron beam. So this is TV. Let's say approximately. This is the, okay, this side is screen. Here's a screen. Okay, right there. So at the back, there's a little thingy that fires the electron. And this electron then hits this thing and it changes the color, and then that's how you create an image. I mean, resolution on this thing is terrible. Okay? Right. However, the beam of electrons, I mean, they fire it at all different directions, but even that has a mass, so it's affected by gravity, so it drops a little bit. So in reality, instead of traveling horizontally, it'll hit the, miss the target about right there. You know what I'm saying? So that's what we are trying to compute here. Okay, so this initial velocity is equal to 5 times 10 to the 6th meters per second. Wow, that's fast. Of course, it's pretty fast. And then this thingy is 0.4 meters, like this. Good. 40 centimeters. Yeah, that sounds about, it's kind of small TV, but you know that the ones that hang on the teacher's classroom so they can show the video bulletin, that kind of stuff. Okay, and we are trying to calculate how far is this drop. You know what I'm saying? Okay, so let's start. So V is equal to, the X is equal to V cosine, that's weird looking V, right? V cosine 0 degree, right? Times T, which is just, let's put a little V naught T. You get it? This is V naught. And then Y, of course, is equal to V naught sine 0 degree T minus GT squared, 1/2 GT squared. Good. So it just turns out to be negative 1/2 GT squared. You with me? Say yes.
Wait, theta is just 0 because it's horizontal, right?
Yeah.
Okay.
Because, well, like this thing does not always fire it horizontally. It actually fires up and down in order to control the entire screen. That's a little like the electron ray gun at the back. But, from the context, it's just, in this problem, it's fired horizontally, so we can measure that drop. How much does the electron drop due to gravity? You know what I'm saying? And it's traveling pretty fast, and it's only 40 centimeters long, okay? Okay, so we have to calculate the T here, right? We'll call it T final. And substituting back, solving for T, so we have X over V naught, correct? And I think we can do this one exact, right? Yeah, that will be 8 times 10 to the negative 8 seconds. So far with me? X is 0.4 and V naught is 5 times 10 to the 6th power. And then, of course, your vertical drop, and then you plug this back in to the original, right, that equation right there. And this one will be negative 3.1, is it 3.6? Somebody confirm this with me. That's weird, 14. 10 to the 14. Meters. Almost negligible. That's why people really didn't calculate this and worry about it too much back then, because it's like nothing. You get it? Good? Questions? Moving on. So in Red Sox field, green monster, extra high fence on the left-hand corner of the park, Fenway Park. Okay, 37 feet high, see how high that is? Okay, and then 315 feet from the home plate. Okay. And then the ball was hit at 3 feet above the ground and just goes over. Let's draw that picture, shall we? So what's going on is this. Let's say about that. And then I'm gonna put green monster, the wall here. Didn't work. Where's my keyboard? Here's my keyboard. It's charged. So I'm gonna move this thing. Like that. That's the green monster. Okay. And then it just clears. I'm gonna make green monsters a little bit lower so we can draw the picture. Okay. So the baseball was hit right here, and then so it has some kind of initial velocity. At some angle, right? Okay, and this is 20 degrees. This is exaggerated pictures, so I can make it go over. Okay. And then this thingy will go. And then just goes over. So basically for our purpose, we can just make it go right there. Okay, that's our picture. That looks ugly. Like that. Okay, now we have to calculate the initial speed. So this v, we have this v, and that's unknown. And we have to figure that out. Okay, and then this is 315 feet, all of x right there. Okay, now the fence is, how high is green monster? That says 37. However, we cannot put entire 37 because the ground is down here. You know what I'm saying? You know what I'm saying? This is at -3. So we have to compensate for that because this is not golf. When you hit baseball, it's a little bit above ground. You know what I'm saying? Waist level, not under. So this launch point is 3 feet above the ground. So this green monster, actually, I'm gonna throw it so that it makes sense to you. This green monster, this fence starts from down here. You know what I'm saying? So that whole thing is, this is 3 feet right here, and therefore this is 34 feet. That makes sense to you? This is my y. Who's confused about the setup? Okay, then we'll start. And this angle is theta, unknown angle theta. So I have this x is equal to v cosine theta t, and y is equal to v sine theta t minus 1/2 gt squared. But instead of using that, do you remember I combined these two? It's a healthy exercise. You should try it at least once in your life instead of memorizing this. But if you eliminate t, then we get this x tangent theta, then minus g x squared over 2v squared, and then secant squared theta. This is, in essence, the football problem we did together in the class. You know what I'm saying? Say yes. Wait, unknown. Did I say unknown angle? No, this is known angle. What was the angle? 20 degrees. This is 20 degrees. So unknown v. Okay, so let's review. Because we don't know t, but it's been eliminated. We know y, we know x, we know g, and we know theta. So we know everything else. Only thing that's still unknown is our v, isn't it? Okay, so let's rearrange it. Shall we solve for this v? So I'm gonna bring that thing over, bring y to the other side. So I have gx squared over 2v squared secant squared theta is equal to x tangent theta minus y. So far so good. Therefore, now I'm going to multiply this cosine to the other side, right? Well, flip both sides. Is it better if I write this thing like this? I think this is better for you, algebra-wise, right? So we flip both sides. So my v squared is going to be g x squared over 2 and x tangent theta minus y, and then times cosine squared theta. Too much algebra?
Yeah, could you explain that one more time?
It's just algebra.
It's too much,
let's-
Mr. Kim.
Okay, which is the best way? Bring this v squared to that and divide by this bang. How's that?
Okay, yeah, that makes sense now.
Okay, go home and think about it. Wait, you're already home, but think about it at home. Okay, I don't have time to teach this kind of algebra. Okay, this is algebra 2 lesson. Okay, how do you not see that? Boom. Okay, whatever. This is calculus VC for crying out loud. Okay, shoving everything into the calculator. So your V, and then take a square root. 149.307239 feet per second. Okay, now caution. What's G here? What's our G at the moment? It's not 9.8. That's meters per second squared. This is 32.
32.
32 feet per second. Let me write that down. G here is 32 feet per second squared. Okay, that you need. Otherwise, you get the wrong answer after doing everything correctly. Okay, different unit, meter, feet conversion. Okay, so this is part A. Okay, and then part B. How long did it take for this? You know, had I read that part B all the way through before I started, then I might as well actually calculated T. You know what I'm saying? No, actually, no, it's still systems of equation. I don't know V, I don't know T. So it's the systems of equation. So no, still this way is better, right? You have to eliminate, so eliminate, then start. You know what I'm saying? So I'm gonna just shove it in here, right? So part B, I'm gonna do B in this corner. So your T here is equal to X over V cosine theta. Too much algebra, children? Can you handle that much, that thingy to this? Okay. No answer, huh? Okay, that's how it is. And shove it in the calculators, and you should get 2.2451 2442, which is kind of forever for the ball to stay in the air. Okay, it takes like usually it gets there pretty fast, but this is green monster. How's that? Good. Okay, let's look at 18 then. Eh? Okay, projectile at 3/4 of this maximum height. In half of the time it reaches the maximum. Okay, so we kind of have to prove the case, right? Okay, let's draw the picture. So we have a projectile here. This is not. What is wrong with my drawing ability? I used to have just such a good drawing ability. And I think I lost it during this pandemic. Blame everything on the pandemic, of course, right? Yeah, so we have this. So this is the maximum, right? Okay, and it attains 3/4 of its maximum height in the half of the time. Half of the time that reaches the maximum here. Does it look like 3/4 to you? Yeah, kind of, huh? By just roughly sketching it, it does look. See what the sketch does for you? Okay. Now, how should we do this? Well, your y, because this is only the y coordinate motion that we are concerned about. This is b sine theta t minus 1/2 gt squared, correct? Let's stare at that for a second. Okay. Now, so we need to find the maximum height. You know what I'm saying? Okay, let's find the maximum height, shall we? So maximum height is when this derivative, let's take a derivative, dy dt, which is known as velocity in y component. So we have v sine theta minus gt, right? And then up here is flat, meaning there's no motion in y direction at the maximum, right? Take a derivative, set it equal to 0 to find the maximum kind of thing. So if we set that to 0, then t here is equal to v sine theta over g. So far, so good. So far, so good. And we don't know any of these numbers here, so we purely have to work with these symbols. Okay, so let's call this T max subscript. Good. Now we'll take half of this and plug it into y. Okay? Because this thing says half of the time it reaches the maximum. So if we take half of this and plug it back here, then we compare it with the maximum height. You know what I'm saying? Okay, so let's do that. So we'll take y and then we'll put 1/2 of t maximum. So the picture-wise, this is t max right there, and this is 1/2 of t max. You get it? You get the idea? Give me some indicator. Why? What is the meaning of your blank facial expression? Like, Okay, good. Okay, and then we'll compare that with. I'm gonna do t max first. This quantity versus 1/2 of t max. You know what I'm saying? And then this one, I want it to be 3/4 of the original one. Okay. So let's do this. So this is v. This is too much algebra, right? Can we do it in our head? Yeah, let's do that, right? Because otherwise it's too much algebra. You know what I'm saying? I'm gonna push this thing down a little bit. So putting that thingy here, so we'll have v squared sine squared theta over g minus 1/2 of this thing is squared. So I'm gonna put 2 here, and then we have v squared sine squared theta over, we have a g squared in the denominator and we have g there, so we have 1g. Too much algebra? Very good. And do you see this is like term? This is 1 minus half. So we have this. Say yes. Say something. Okay. That's how it is. Huh? Now we're going to put 1/2 of T max. So half of this is just basically putting 2 in the denominator now, isn't it? Do you see where this is going? So if we plug that in here, then we'll have this. And then we have 2 here, so 2. Do you see that? And minus the other one, we put 2 in the denominator and we're going to square it, right? Okay, let's be careful. We square this, so we're going to have 4 in the denominator. So far so good, and then we have another half. So do you see this is 8? Say yes. Okay. I just write it and simplify it, otherwise children might get lost. Common denominators, 8g children, right? So you multiply this by 4 and multiply this by 4, then you subtract. Good? So 4 minus 1 is 3, v squared sine squared theta. Okay. Then is the question, is this thing 3/4 of that thing? Let's check. So you imagine multiplying 3/4 here, then do you see they are the same thing? Wow, amazing, isn't it? Let's erase, oh no. I wanted to erase this evidence so that, oh no, this is under recording, so thank you so much for that. Destroying evidence. See, once you leave a video evidence of something, then you cannot really destroy that evidence. So now we can conclude that y at half of the time t max. Notice that we didn't use any numbers, right? You still don't know what the angle, velocity, any of it is 3/4 of y at t max. How about that? EDA? Okay, maybe it's just me. Well, then we'll look at really beautiful problem. Oh, this is mother of all projectile motion. Okay, I'm gonna copy the picture. Not that picture. Can I? No. Okay, I'm gonna have to. How can I just make a copy of that picture? Okay, why don't I animate it? I have this thing, right? I need the picture after all, so hey, let's animate. Hopefully this thing is, oh no, do I have that file in this computer? That's another annoying thing about not having projectile motion. Do you see projectile? No, I don't see projectile. Okay, I don't have it. Well, I guess I'll throw it. Okay, so what's going on is this. We have this situation. But we are not firing this thing at horizontal range. This is actually decline. We have this thing going on. Okay, and then we give an initial velocity. So how high should we launch this thing? You know what I'm saying? In order to maximize this range downhill, so it's like that. We want to maximize this thingy. Ew. Isn't that horrible? So this is V. And then we have this, the problem calls this angle alpha and this angle beta for some reason. So we'll go with that. Okay. Huh. Ideas? We will start by writing down these projectile motion equations, right? X is equal to V. Sometimes I put V now, sometimes I put context, right? That means cosine, this time alpha t, and then y is equal to V sine theta alpha t minus 1/2 gt squared. Good. Okay, so that describes this curve, right? Now, I need something to describe this line. Somebody give me the equation of this line down here. Oh, come on, this is a linear equation. Oh, this is calculus BC, for crying out loud. Give me the equation of line. Y is equal to?
Tangent beta.
X tangent beta.
Tangent beta, oh my God. The reputation of this high school has been just restored. Tangent beta, right? Do you know that relationship between that angle of elevation or depression and the slope is tangent of that angle, right? Y over X, which is slope. You get the idea? Do I have to say rise over run? Delta Y over delta X is good enough in calculus, right? Okay, good. Whew. Okay. Faith has been restored. I need a drink to celebrate this moment. Coffee will have to do. Because I was losing faith for a while here. I mean, your test average, I'm not going to say the number here, but that just tells me, wow, that's like, this is historic, and blame it on pandemic and all, but okay. Okay, so we have this. Let's just write it down and think about it. Y is equal to tangent beta X, okay? Let's stare at these things. What does it look like? What are we looking for? We're looking for this point, right? We want that coordinate, X and Y. Oh, by the way, don't try to get some kind of a downhill range and then try to maximize. Oh my God, that's an algebra nightmare, and you have to take a derivative of that. But if I can maximize the X distance, X coordinate, then I have maximized this downhill range as well, right? Okay, so we'll just maximize X. So what does it look like? No idea. Oh my God. This is really too much algebra now, isn't it? How do you find the intersection of the two functions? These are still functions. This is one curve and this is another curved line. How do you find the intersection of two functions?
Set them equal to each other.
Yeah. This is systems of equation now, isn't it? But unfortunately, it's not just X and Y. This is X and Y, but we have X and Y and T. So this is three-way systems of equation any way you look at it, right? I have two different versions on the Dropbox note. One version is eliminate t between these two and we have that equation, and then set that equal to this. The other way is we can substitute this x into that thing, this y into that thing, then work with this. Which version would you like to see? Or should we do both? They are both long.
Second one.
Second one? Okay, with the second one. So this thingy, this expression, we are going to put here, and that expression we are going to put here, right? And let's see what we get. I have to draw these arrows now, right? Okay. So we have v sine alpha t minus 1/2 gt squared on the left-hand side, and on the right-hand side I have tangent beta, right? And then our x is v cosine alpha t. Good. Okay, then can we, oh, I can see I skipped a line, right? And Dropbox note. Okay, I'm not gonna do that. I'll just do it. Take every possible step. Okay, these two don't mix, by the way, right? So I'm gonna bring it over. So I will have v sine alpha t, and then minus cosine, which will, yeah, I'll write it like this, v cosine alpha tangent beta, right? And then t, that thingy, just purely that thingy, minus 1/2 gt squared is equal to 0, correct? I'm going to common factor t, so t out here, and wait, this is a computer, so I can, hold on. See me take the lazy way. Why does it end up there, right? And then erase that t and erase that square and erase that t. So I just factored out t. What the hell? You know, when I take the lazy way out, it usually takes longer. So it's like, do as I say, not as I do. Don't try to take shortcuts and end up wasting more time. So far, so good. So what I have is either t is equal to 0, or that t is equal to 0 is this corner right here, right? That's not what we are looking for, because we are trying to calculate the time to get here, right? Say yes. Okay. Or, and the other one is this thing, right? So t is equal to, can I do that much in my head? It's not that hard, right? Right. V common factor, and then 2 up here, so 2v over g, and then I have this thing minus that thing, right? Sine alpha minus cosine alpha tangent beta. Too much algebra? Now everybody's afraid of saying what happened, right? So we'll say you all got it, right? Okay. Whoever's watching this video, they all got it. They're perfectly on top of it. Okay. Now, so this is my time that it takes me to get to this point. Where do we have to substitute this now? What are we trying to maximize? The x coordinate, right? So we take that and shove it right here. You get it? So all I have to do is just multiply v cosine theta here, right? Please tell me you can do that much. Okay, so x is equal to, okay, I'll do copy and paste again. Cosine alpha times Hey, wow, I got it in one take. Like that, right? Then I'm gonna distribute. So I will have v squared, right? 2v squared over g, constant out of the way, cosine alpha here, so I have sine alpha, cosine alpha, minus, I'm going to multiply, so this is cosine squared alpha and tangent beta. You know that these two don't mix, right? Different angles. With me? Say yes. Okay. Now, guess what the next step is? We're trying to maximize x, and this is calculus. That should be an enough hint.
Derivative.
Derivative, of course, right? Oh, yikes. Derivative with respect to what? What are we trying to find? What's our variable here? It looks like we lost all of our variable. What are we trying to find? Sometimes you start off in a journey in search for something, and then you're like concentrating too much on the survival, and then you lost, like, what are we doing?
Is it angle of elevation?
Yeah, we are trying to find that angle alpha that maximizes. So we actually imagine we are varying this thing a little bit, and then this thing changes. You know what I'm saying? So we'll treat alpha as variable now. We vary alpha. You get it? And then this downhill range will vary. Those of you who play golf, if you have a downhill tee box, are you supposed to launch this thing higher than you? Let's say you have your maximum angle. In case of my driver, about 25 degrees, 30 degrees, this gives me the maximum distance. And if I have a downhill, am I supposed to launch this thing higher or lower? What do you say?
Lower.
The common sense should tell you that this thing should be a little lower. You know what I'm saying? Okay, let's reverse the situation. If I have an uphill, right? And then I don't want to hit it too low, then it'll just go into the ground. You know what I'm saying? So I have to adjust it and go launch it higher, assuming that you have this ability to change the launch angle on a tee shot. But hey, right? So it has to be a little lower. You see what I mean? But, God, I hate product rule. This one is okay, but product rule, no, I don't want to do that. So guess what I'm going to do? 2 sine alpha cosine alpha. Oh, that looks convenient, eh? I'm going to distribute that too. So what we have is v squared over g, and then 2. Oh, I just write it as sine 2 alpha. You get it? You still remember your identities? And then I just put this 2 cosine squared alpha tangent beta. Now I'm going to take a derivative with respect to alpha. So v squared over g is constant, and this, of course, becomes cosine 2 alpha, chain rule 2, and then cosine squared. This thing is minus 4 cosine alpha, and the chain rule, make that plus sine alpha. You with me? Tangent beta. Say you're with me.
We're with you, Mr. Kim.
Thank you. That's great. Now we set this thing to 0 in order to find the maximum. Okay, that means this thing inside 2 cosine alpha is equal to negative of 4 cosine alpha sine alpha. Wait, that's another cosine, 2 sine cosine, right? So why don't I change that and make it 2, and then sine 2 alpha. I think I lost 2 alpha. Oh, that alpha looks weird. And then tangent beta. Oh my God. Tell me you're still with me. We are solving for alpha. Divide, divide. So what we have is sine over, divide by 2 while we are at it. So this is tangent to alpha is equal to the other side, negative cotangent beta. Still with me? One thing I have to note, I just said that's beta, right? But that's downhill. Is that negative beta? It all depends, right? If you set this as a beta is a positive number and negative beta, then this thing, you need a negative sign in front of it. So we are missing negative sign all throughout. So let's not do that because this is unthinkable to go back and change it. We'll just say this is a general angle beta. So beta itself is negative. You know what I'm saying? That way, actually, it works for downhill and uphill. This beta could be up here and down here. You know what I'm saying? Yeah, that's more general case, so this is better. Okay. How are you going to solve this trig equation? Okay, fine. Cotangent is a odd function or even function? Odd function. Good. Okay, do you remember, I want this thing to be tangent, not cotangent. So we have to use co-function identity, right? How did the co-function identity work? Pi over 2 minus that thingy. Good. Good. Say yes. Okay. Now we can say 2 alpha is equal to pi over 2 plus beta, eh? That's plus, minus, minus gives you plus, children, who are weak on algebra. We're almost there, right? Divide by 2. So therefore, finally, alpha is equal to 90 plus beta over 2. What does that mean? Okay, let's go back to the picture and look at it. 90 meaning this thing, right? This angle from horizontal, that angle, 90 degrees, plus this beta, divided by 2. That's the average of the two now, isn't it? What does the average look like? Okay, let's go back to the general case. If beta is 0, then we are back to this horizontal range, right? So let's apply it. 90 plus 0 divided by 2. That gives you 45 degrees. Remember that? So if this beta is positive, then we have to go a little bit higher. If this beta is negative, then that's average, a little bit negative, a little bit down. You know what I'm saying? So it turns out this, whatever we got here, happens to be the angle bisector. Wow, now we are mixing this with geometry, right? Angle bisector between this vertical and that thingy. Do you see the average is angle bisector, right? What's the average of 30 degrees and 60 degrees? 45 degrees. You see that's an angle bisector between the two? So by what percentage should you increase the initial speed to double the height and the range? Okay. So let's write down this projectile motion thingy. So we have this option, x is equal to v cosine theta t, and then y is equal to v sine theta t minus 1/2 gt squared, right? But then, do you remember the one that I combined for you, right? So if I combine the two, then we have this. Y is equal to x tangent theta, and then minus g x squared over 2v squared, and then secant squared theta. It's a judgment call on which one to use, right? And one of the consideration for this judgment is, do you ever need the time here? Nope, they don't ask you about the time. You don't need to know the time. So might as well just combine the two. This is a nice x and y. You know what I'm saying? You know what I'm saying? Okay. Now, here, you have to double the range. Let's do the range first, okay? So if you want to double the range, that means your y is equal to 0, right? So far so good. Range meaning when this thing lands on a flat ground. So, well then we just solve for x. So setting this thing is equal to 0. Can I factor out x here? Then we'll have tangent theta minus gx over 2v. I'm gonna write x out there, square. We change it like this. You can square theta in here because we are solving for x. You know what I'm saying? Okay, so what we have is x either is equal to 0 or the other one, this, right? So x is equal to, this is equal to that thingy, so multiply reciprocal. That's, I fear that will be too much algebra. Let me take my time. So we have tangent theta minus 2 secant squared theta over 2v squared x. Well, these are equal to each other. Good. So my x here is equal to, flip it over and multiply, that's v squared, that looks weird, v squared. So we will have 2v squared over g, so far so good? Say yes. And then we are multiplying, this is cosine squared in the denominator, and then we are multiplying, maybe I should have written it then, right? Let me write it this way. 2g over 2v squared, and then let's write it like this. Here's the x, ugly handwriting, and then cosine squared. Maybe this is easier way to see. So you multiply cosine, you know what I'm saying? So tangent is sine over cosine times cosine squared, then we have sine theta cosine theta, eh? So far, so good. So far, so good. Okay, let me push this thing down. We don't need it, but this is my habit of 2 sine theta cosine theta. That gives me nice sine to theta. And then I'm gonna put v squared here, okay? Here's what I have done here is this. I found the relationship between x and v, and it's quadratic. You know what I'm saying? So I want to double the output, right? So what I have to do is compare x versus 2x. You know what I'm saying? So in order to double, the range, in this case x, right? When y is equal to 0, what we do is this. compare this with this. You know what I'm saying? And then we figure out what is it going to, no, I don't want to do it that way. So what kind of V value will give me double of this quantity? How do I want to explain this? I know the answer is the square root 2 times V1. Shoot. You guys know what I'm saying, right? If I put square root 2 times V, then you see that will give me exactly double, right? Because square root 2 and then I'm going to square it. I just don't know how to explain this. How should I explain this? Knowing the answer. Look.
You couldn't say like 2x equals, like, or kx equals something, and then you just have v times a constant.
Let's try that. That actually sounds like a pretty good idea, right? So what we want to do is we want to have 2x, right? Double this side. And then the other side, we want to have 1 over g sine 2 theta. This is just a constant, right? And then we want to have k v square, and we want to know what that k is. Yeah, that sounds about right, right? Okay, so then what we have is substitute this thingy back. So we have 2 over g sine 2 theta v squared here, and the other side becomes 1 over g, and then sine 2 theta, and this is k squared v squared. You know what I'm saying? That was actually a pretty good idea. And then everything else cancels, so that it tells you 2 is equal to k squared, meaning k is equal to square root 2. You get it? Do you know what I'm talking about?
Yeah, I got it.
So if we plug in here instead of v, if we put, so is this, using x as a function, and then if we put this in as an input instead of just v, then what that gives us is this, 1 over g from here, sine 2 theta, and then we have square root 2 v squared, right? And that just doubles everything. See, this is exactly double as before, right? So we want square root 2 times more. And then, of course, square root 2 is 1.414. So our answer should be let's do it in percentage, 41.4% more, right? Because the question says, what percentage should you increase? So this thing. How about that? So you don't have to really, see, idea is this. If you double the initial velocity, you get 4 times more range, right? So you only need to increase the initial velocity by 41% in order to double the range. You get the idea? You don't get the idea? What is the meaning of that weird facial expression? Well, then what about y, right? Okay, let's think about y here. Y looks like this, right? Oh, this is quadratic in terms of x, right? instead of doing that, the maximum height is when this thingy is half, right? So I'm gonna plug that back in. So now I'm gonna change the color for max y. Okay, we'll do that. So we have max at x is equal to half of what we have, right? Downrange, this is the maximum range when this thing lands. Why don't I draw the picture for you? I think picture is healthy to understand what's going on. Okay, so what our situation is this, right? And this point is when x is equal to, what was it, 1 over g sine 2 theta v squared. Good. So then we need that maximum. This is maximum y, isn't it? So this is when x is equal to half of it, 1 over 2g, and then sine 2 theta v squared. You know what I'm saying? Say yes. So that's what I mean by at max y, x should be 1 over 2g sine 2 theta v squared. So far so good. And then we substitute it into this y equation, which was x tangent theta minus, I wish I can remember, let me look it up, gx squared over 2v squared and then secant squared theta. We substituted theta. Okay? Okay, so we substitute that thingy here and there. Okay, let's see what we get. So our x is this, and in order to simplify, I'm gonna convert this into sine and cosine. See, I'm gonna do it here. Sine 2 theta, this tablet is frozen. Sine 2 theta is 2 sine theta cosine theta, so I can actually cancel one of them and then write down sine theta cosine theta and v squared, eh? Okay, let's substitute that. So I have here, I will have 1 over g and then sine cosine, and then tangent is sine over cosine, so we have sine squared theta, and then v squared. So far so good. Okay, minus, and then plug it in here. So I'm gonna have to square that, and then plug it in. So I will have g squared, and then, you want me to write this down? Why don't I write the whole thing down? Because I get a feeling that I'm losing 2/3 of the class. I'm gonna write it down. So 1 over g sine theta cosine theta v squared, all of that times tangent theta, which is sine theta over cosine theta, is the first term, minus g over, I'm gonna write this thingy first, so 2v squared and cosine squared, that's what secant is, and then I'm going to multiply that thingy square. So I will have 1 over g sine, well, square, cosine square, theta's missing, and then v to the fourth. You see what that does? Okay, let's simplify that gigantic mess. So here I will have 1 over g, cosines cancel, so I have sine squared theta v squared. With me? And then here, v's cancel, so one of the g cancels, so I have 1 over 2g. Cosines cancel, so I have sine squared theta, and then that v squared cancel, that's v squared, so it's still this. Wow, that simplifies nicely now, doesn't it? So what we have here is, this is 1 minus half. You get it? Look, this is still only quadratic in terms of v, just like that one, isn't it? So in order to double this, we still need to just increase it by square root 2 times this v. You know what I'm saying? So we just need to I'll just say this is same as before, right? That's ugly handwriting. Not that much better. So same as before, we need 41.4 degree. Oh, my tablet is dying. Let me just plug it in. Okay, just saved it. Increase. How about that? Good. Question? Okay. Y'all physics people, don't you wish you had this skill when you're doing projectile motion in physics class? Yeah, okay. Now, number 26, and you just wanted the A? Does anybody want the whole thing while we're at it? Okay, so we have a baseball that hit 2.5 feet above the ground, and it leaves the bed, the launcher. So, okay, this question itself is, I didn't come up with this question, but there's like instant burst of the wind that just knocks the ball down, right? So just it slows the ball down by that much, and then it disappears, right? Okay, 15. Find the vector and parametric form of the path of the ball. Okay, let's do this. Okay, I'm gonna draw this picture. So what we have is this case. Okay, and then ball is launched here with the initial velocity 23 degrees. It's exaggerated picture, but let's say that's 23 degrees, okay? And then this ball is going to take a path and then fly like that, right? And then we're trying to see whether this will clear the fence or not. So here's a fence. Is that high enough? Is what we're trying to calculate, okay? Okay, so we can just set up regular parametric equation, but they want the vector form. So why don't we just do it as a vector thingy, right? So do you remember how I set this thing up? Your A of t, which is the second derivative, right, is equal to just negative j vector, right? Now we have an initial condition. Initial condition with number 1 is this v at 0. It used to be whatever the initial velocity, right? So initial velocity is cosine v your initial, whatever they give you, which is 145 feet, right? So V cosine theta, and this theta right here is 23 degrees. I vector plus V sine 23 degrees J vector. This used to be it, right? But that initial burst of wind, which is ridiculous, in I direction, I wrote J. This becomes our initial condition. You know what I'm saying? I mean, this is totally physically unrealistic. You cannot have that much gust of wind at the time the batter hits the ball, and that wind just slows down the ball that much, and then it disappears. Like, ridiculous. But let's say Superman sneezed at that instant or something like that. Okay, and then, of course, this is equal to 0. We are still setting this up as 0. Okay, now your ground is somewhere below here, right? Because 2.5 feet above. Okay, so that we have to adjust this fence later. 15. This is 15, but this thingy is not exactly 15. This has to be 15 feet minus 2.5 feet. You know what I'm saying? Because this thing is not on the ground. This is not golf, right? So baseball is hit around the waist high. So that's about 2.5. So far so good? Okay. So it works out exactly the same as before. If we take antiderivative, then you get V. And that is negative GT J vector plus C vector, right? So if you take the initial condition at V at 0, you get 0 here, so you get just C vector, but that has to be this thingy, right? So I'm gonna put V cosine theta. Do we want number? No, we don't. V cosine theta minus 14 I vector, and then plus V sine theta. J vector. So far so good? So far so good? Okay, now then we find another antiderivative, so that gives you R vector. Oh, we have to plug it back in. So our V T is this thingy, V cosine theta. That's ugly cosine, hold on. Cosine theta minus 14. And then I vector, and then we have plus V sine theta, that part, and that combines with this minus GT J vector. Good? Are you with me? Okay, then take another antiderivative, so we get R here. And this thingy becomes V cosine theta minus 14 times T. They are all constant. I vector plus this one, V sine theta, T here, and then minus G T square, therefore 1/2. So far so good. And J vector plus D, another constant. And then if we plug in 0 here, all of that becomes 0, so we just have D is equal to 0, 0 vector. So this is 0 vector. You get it? So there you have it. You know what I'm saying? This is the A part. So let's come back, and in summary, because what we used to have is just this V cosine theta. and nothing else. And this looks exactly same as before, right? I'm gonna write it down, x and y. So this x used to be just v cosine theta and nothing, t, and t. Don't write that t down, I'm gonna erase it right back. And y used to be v sine theta, t minus 1/2 gt squared, right? But only thing that changes is that initial velocity here. So only thing that changes is we just add this component. You get it? And then everything else works out exactly the same way. Of course, then you're wondering, why the heck didn't they have this wind continuously blow? But that's a nightmare differential equation. Okay, then you have to change that to acceleration here, right? Then you have to add that component in here, and that creates the acceleration in x direction, and that's realistic. So if there's a wind against you, I mean, this just drops the ball. It's not even close, because I play golf every weekend, so I know if I'm against the wind, this thing shortens the range quite a bit. For some weird reason, if the wind is in my back, it doesn't really help me the same amount. I don't know how that works, but okay.